This is part 3 of chapter 3, the Curry-Howard correspondence. Imagine you have a program, and in this program you have code like this. It means that at some point in your program, in the expression, you are able to compute a value x of type t. Now, of course, we're assuming that your program is correct and running, and your expression is being evaluated correctly. So, if so, you have a value of type t. Let's denote this proposition by ch of t, meaning that code has a value of type t. The Curry-Howard correspondence is a correspondence between types and propositions, and also between values and proofs. On the one side, there is program code in a functional language. That program has types and expressions that have those types, or values of those types. On the other side of the correspondence, there is formal logic, which has propositions, and these propositions can be true or false. The formal logic has proofs of propositions. So true propositions follow from axioms or from other already proved propositions. So in this tutorial, I will explore this correspondence using Scala as usual, as in all my lectures. So what is this correspondence? Let's look at this table, which summarizes this correspondence. So as we agreed, the proposition that corresponds to each type, not to each value, but to each type, such as integer, floating point, double, string, and so on. So each type corresponds to a proposition. The tuple type corresponds to the situation that you have computed two values. So let's say tuple of a and b. It means that if you computed x, which has the type tuple of a and b, it means you have computed some a and you also have computed some b. You cannot have a tuple if you don't have both parts of the tuple. So the proposition, therefore, is that your code has a and also your code has b. So this is a logical AND operation on the propositions, also called conjunction. The either type corresponds to the situation that you have computed maybe A or maybe B, but not both. You certainly have computed one of them, though. You just don't necessarily know which one. So in the logic, it means you have computed A, so code has A, or code has B. So this is a logical OR operation on the two propositions ch of A and ch of B. So in other words, ch of tuple AB is equal to this. Ch of either AB is equal to this. What is the significance of a function type? Suppose you have in your program val x colon a to b equals something. It means you were able to define a function or compute a value of function type, which is the same thing. This function takes a and returns b. So if somebody gives you a value of type a, you will be able to produce a value of type b. In other words, if your code, maybe at some later point, has a value of type a, then your code will also be able to get a value of type b. So in the logical language, this is an implication. Again, a logical operation of implication. This proposition implies that proposition. So if you have an A, then you also can have a B. It doesn't mean, though, that you have an A. So having the function expression doesn't mean you have an A. You have any values of type A at all. But should you get them at any point, you would be able to apply this function to them and get the B, or the values of type B. The unit type corresponds to the true proposition which is identically true. Proposition that is always true, regardless of anything you have computed or not otherwise. So why is that? Because it is because you always can have a value of unit type. All you have to say is val x colon unit, or without a type annotation, equals the empty parentheses, the empty tuple. You don't need any other values to be able to compute unit. You can always have it. So code has unit always, regardless of any other values that the code has or doesn't have. So it means that the proposition that code has a value of type unit is always true. Nothing is a special type defined in Scala that does not have any values. So your code can never have a value x of type nothing that's equal to something. And so the proposition that your code has a value of type nothing is a false proposition, is always false. So in this way, we can see the correspondence between types and propositions. And the interpretation of these propositions is that your program can compute a value of a certain type. I will be using short notation for these things. This notation is not always convenient. This is Scala syntax on the left. In the middle, this is syntax of formal logic written in English. In formal logic, one uses special symbols for and, or, implies, true and false. And these symbols are not always convenient when you work with programs. Because actually we're not going to work so much with logic as we were going to work with types. So the short notation can be used at the same time for types and for logic, for types and for propositions. In the short notation, we just represent the tuple type or the logical conjunction by this product symbol, direct product in mathematics. We represent the disjunction or the or operation by the plus symbol or this logical disjunction symbol. And I will use both in different contexts. I will use this only when talking about logical propositions. I will use this when talking about types. And since we're going to be talking about types most of the time, we're going to be using this most of the time. And why it is a plus, I will explain in this tutorial. There's a significance to choosing the symbol plus and the symbol of the product, rather than logical symbols of conjunction and disjunction. The implication, I'm going to also use this arrow because we already have the arrow that's good enough. Instead of true and false, I'm going to use 1 and 0. So unit is 1 and nothing is 0. Well, I'm not going to have a lot of experience dealing with values of type nothing because there can't be any such values. But sometimes it's convenient to have the notation for this type. So if we have a type parameter in a function, it means that the function is a value defined for any such type. And in the logic notation, that is denoted like that, for all t. In other words, for all propositions t, something is true. In the program, it means for all types t, we can get that value or that function. Here's an example. This function in the Scala syntax takes a value of type A and returns a tuple having two values of type A. Now, the type of this function is this expression, is for all types A, because A is a type parameter variable, we have this function type. In the logical language, this corresponds to this logical proposition. For any A, from A follows A and A, because I'm using this symbol for the logical AND. Now, if you think about this proposition, it is valid. Indeed, no matter what A is, if A is given, then A is true and A is true. Now, this proposition doesn't seem to be very deep. Correspondingly, this function is not very interesting. It just takes a value and duplicates it, repeats it in both parts of the tuple. Not a very interesting function, admittedly. It's just a very simple example that illustrates the correspondence between types and propositions. As another example, let's consider a disjunction type, which is in Scala defined using traits and case classes. So the first example, I have a simple disjunction type that represents some kind of user's action in some kind of application, let's say. And there are three cases that the user can set the name, and that variant, that case, has two parts. Then the user can set email, that is one part that is a string, and here it can set user ID with a long integer value. The short notation for this type is this. You see, all the names are stripped, they are omitted. So user action, set name, set email, first, last, and so on. All of that is omitted from the short notation. Only the bare types are shown. And you see the disjunction very clearly, and you see the parts of each part of the disjunction. So the disjunction has three parts corresponding to these three case classes. The first part has two strings, so it's a tuple of two strings. And the second part is a single string, and the third part is a single long integer number. In this way, we can write short notation for the types that we use, making the type structure much clearer. At the same time, we lose the information about names, and that information is useful, of course, while writing the program, because it reminds you what all these parts mean. What is this string as opposed to that string? But when you talk about types and their properties and the properties of functions, the logic of types, when you reason about types, it is not helpful to know that this is the first name and that is the last name. It is helpful to know that you have a string and you have another string. That's why we will use the short notation for reasoning about types at an abstract level. And once you have finished that reasoning, you translate the short notation into Scala code, putting in all the names according to the actual significance of these values. This is, of course, very helpful for programmers to put in these names. As a second example, consider a parameterized disjunction type, which I called either 3. So it's a disjunction of 3 possibilities, left, middle, and the right. And this is a very simple generalization of the either type. So the short notation for it is like this. It is just a simple disjunction of A, B, and C. And here I introduced another notation for type parameters. Type parameters are written as superscripts at the type constructor. So the type constructor either 3 has 3 type parameters, and they are written in the short notation as superscript. This is a notation I invented. If it proves to be useful, I will keep using it. So far it's been pretty good. However, I'm open to changing it if there's a better notation. In this tutorial, I will use this notation. So, what can we get out of this correspondence? So I would like to show you several very useful things that we get once we realize that the correspondence exists between types and propositions, and alternatively, or rather, also a correspondence exists between proofs of propositions and program expressions, actual code. So there is a lot of useful value to be extracted from this knowledge, and so that's first example of this value is that we have in logic various theorems, or valid formulas as they are also called. Formulas that can be derived in logic from axioms using the rules of derivation. Each logic has certain axioms and certain rules of derivation, and then those formulas that you can derive in the logic are valid. That is the terminology of formal logic, and they are also called theorems of logic, if you wish. So these are on the left in this table some examples of theorems, valid formulas of logic. So for example, this is actually an axiom that for any proposition A, if you have that A is true, then A is true. Now, the second example is also an axiom of logic that truth follows from anything. In other words, you don't need to prove a proposition that is identically true. I'd like to stress that follows from, it has a very specific technical meaning in logic. It does not mean that it somehow causally follows, or that, A is a special proposition that causes this to be true. This is not the meaning of of implication of this symbol. This is the implication symbol. The meaning of this symbol is that if we can prove that A is true, we can prove that this is true. So the meaning of the implication symbol in this logic is that if we can prove what's on the left, then we can prove what's on the right. So if we can prove A, then we can prove A. Well, that seems to be obviously true. If we can prove A, whatever that A is, then we can prove the true proposition. But that is also immediately obvious, because the true proposition is identically true. It does not need to be proved. It's already true. And so it doesn't matter what propositions we already proved here. We can ignore all those proofs and just have the true proposition. Now, here's another example. Oh yeah, I wanted to show the code for all this. So what is the identity? Well, this is the identity function. This is a standard library in Scala. Identity function defined, let's say like this, takes an argument x of type A and returns a value of type A. Of course, it just returns x. So the correspondence between proofs and code, I'd like to illustrate in this table, is that if you have a proof of A, it means you have a proof that your code has a value of type A. Remember the interpretation of our logical propositions is that code has a value of type T. So all of these in the short notation, A means CH of A, so code has A. So what is the proof that code has A? Well, it's the value x, the value x itself. The value x is the proof that we have computed a value of type A. So if you have a value x, it means of type A, it means you have proved the proposition A for your code. And like I said, all these propositions are specific to each program. So in each program, some of them can be true and false. In other programs, others will be true or false. So let's keep that in mind. So in a specific program, if you have managed to compute a value of type A, then in logic it means you have proved that proposition A is true. CH of A is true. So proofs are expressions. X was probably computed by some other part of your code through some long expression, let's say. So that's the proof. That corresponds to the proof in the logical, on the logical side of this correspondence. And now, if you have a proof of A, then you're supposed to produce the proof of A if you want to prove this proposition. Well, that's obvious. You just reproduce the same proof. You were just given a proof of A second ago. So you just give that proof back. So you see there is a direct correspondence between proofs and code. Let us see on further examples how this works. Here's a proposition that if you have a proof of A, then you can prove the true proposition. The code is that you take this x, which is a proof of A, you ignore it and return the unit value. So you ignore this x, which is the only way that you can do this. You cannot use this x in order to prove that you have unit, because you already have unit. Unit is this. There's no more information in unit. You don't need x to get unit, and you cannot actually use x to get unit, because the only thing you have here is x, so there's no way for you to make a unit value using x. You have to ignore it. And unit value, there's only one of them, so no information from x can pass into the unit value. So in this way, this code corresponds to the proof of this proposition, that whatever you have previously proved, you can prove truth by ignoring the proofs that you had before, because truth is already true. It's a proposition that's identically true. Let's just look at the next example, a slightly more complicated example. For all A and for all B, if A is given, then A or B can be proved. So if a proof of A is given, you can prove A or B. How do you do that? Well, you reproduce A, you reproduce the proof of A, and that's good enough. You will never be able to prove B, because you don't have any proofs about B. You only have a proof of A, and so you're always going to return the left side of this disjunction. But that's good enough. You have proved the disjunction. What does the code do? It takes x, which is of type A, and returns left of x, which is a value of type either AB. It's one of the case classes from either. So left of x is of type either. So you see this is exactly equivalent to the way we proved this proposition. We don't try to produce any values of type B, because we can't. We cannot ever produce right of B in this function, because we will never get any B. But we can produce left of x, which is in A, in the left side of the disjunction, and that's good enough. The next example is this. If you have A, or a proof of A, and, remember this is logical and, if you have a proof of A, and if you have a proof of B, then you have a proof of A. How you can prove A? How do you do that? Well, you already had the proof of A, so you ignore this proof of B. You can't use it in any case. You reproduce the proof of A that you have been given. What does the function do? A function takes a tuple of type AB. It takes the first part of the tuple, ignoring the second part. And the first part has type A. There's nothing else you can do here. You cannot produce A in any other way, because A is an unknown type. So the only way you can get an A is to take the first part of the tuple. Next example is more complicated. From A follows, from B follows A. Now, I have said in my previous tutorial that we have a syntax that the implication symbol associates to the right, and so these parentheses are unnecessary. I just wrote them here for clarity, but they are unnecessary in our syntax, and later I will stop doing this. So how can we prove this theorem? This is still a valid theorem. All these examples are valid theorems. How do we prove this theorem? So we have a proof of A. If we have a proof of A, then we're supposed to return this. What is this? This is something that will give you a proof of A if you give it a proof of B. If you give it a proof of B, so this thing is something that can produce a proof of A if somebody gives it a proof of B. How will it produce the proof of A? It will take this one. It will ignore this proof of B, and it will just reproduce this proof that was given previously. That is how it's going to be done. Accordingly, the code does precisely the same thing. It takes an x, which is of type A, and it returns a value of type B to A by taking an arbitrary y of type B and returning this x. So we are ignoring this y, and we return the x that was given early on. So you see, this is exactly one-to-one. The proof of this proposition is exactly the code of this function. The proof of this proposition is the code of this function, and so on. So we have this Curry-Howard correspondence, which is between types and propositions, and between between code of functions, code that has a certain type, and the proof of that proposition. Importantly, invalid formulas cannot be implemented in code. So valid formulas can be implemented, invalid formulas cannot. Here are some examples of invalid formulas. They're invalid in the sense that they are not theorems. They cannot be proved, and they're false. In this sense, they're not valid as statements, as propositions. Here's an example. For any A, from 1 follows A. This cannot be proved because you're supposed to produce a proof of A out of a proof of the identically true statement. Well, identically true statement doesn't need any proof. So if you say that you had this, you say nothing. Everybody has this. Nobody needs any work to prove this. So you're basically trying to produce a proof of A from nothing. And A could be a false statement. So you couldn't possibly have this. You couldn't possibly produce a proof of any statement out of essentially no information. Another example of a non-valid, non-theorem, non-invalid formula is that, now I just want to be sure that you understand invalid not in the sense of syntax. The syntax here is correct. It is not a theorem. It is a false statement. So for all A, for all B, if you have A or B, this is the OR symbol, the logical disjunction. If you have A or B, then A follows. Well, that is not true, because if you have A or B, it doesn't mean you have A. You might have B and no A at all. And then you would not be able to produce a proof of A, because you only have a proof of B, and A and B are completely different. So A could be false and B could be true. You could not possibly produce a proof of a false statement here. Another example of invalid formula is this. So from A follows A and B. So how are you going to get B? You're supposed to produce A and B. So A you have, but B you don't have. Again, the same problem. You're supposed to produce something you don't have. This is when propositional logical statements are invalid. They cannot produce a proof of some formula without the required information about that formula. You cannot just produce it out of nothing for any B. Very important. This is supposed to be working for any A and B. It's not possible to do that. Another example, slightly more complicated, of why things cannot work is this. For any A and for any B, if you have this, then you're supposed to produce A. Now, what does it mean you have this? This is a function or implication in the logical realm, right? We're in the logical domain. So this is implication. So all you know is that if someone gives you a proof of A, you can produce a proof of B. You cannot get a proof of A out of that knowledge. So that knowledge is actually the knowledge of how to take a proof of A and make a proof of B out of it. It is not knowledge about how to prove A. And so you cannot possibly derive A from that knowledge. Derive the proof of A from that knowledge. You cannot. Now, I am telling you why they are false. In order to prove that they are false, you need to study formal logic. And this is this is something that can take a long time and not necessarily bring a lot of illumination here. You would have to prove essentially that no combination of axioms and derivation rules will produce this formula. And this is not a very obvious proof, but it's kind of obvious why you cannot prove this. To me, this is obvious, because in order to prove A, you need information about how to prove A. And all you have is information about how to make a proof of B out of an already existing proof of A. So you cannot get that. So, as I said, valid formulas can be implemented in code, invalid formulas cannot. So suppose I have a formula, and I want to decide whether it can be implemented or not. So actually, since I'm interested in applications in functional programming, I'm actually only interested in the question of writing code. So my question, therefore, is, given some logical formula or type, can I implement it in code or not? And if I can, how? So this is the central question that I will be dealing with in this tutorial, among other questions. Here's an example. Now, these formulas so far seem to be kind of trivial. This might be a little less trivial. Now, here's an example. I have no idea how to implement this or if it's even possible. Very complicated type. If you interpret this as a type, so these are two type parameters, a and b, and then there's this higher order function of order like 5. So it's completely unclear at first sight whether this formula, this type expression, corresponds to a function that can be implemented, let alone why you would like to use that function. What is the usefulness of this function? But it turns out these functions can be used for certain cases, but right now let's concentrate on the question of how we get this code. So suppose we know we need this type. How do we get this code? Turns out mathematicians have studied this question for a long time. Mathematicians were only studying the logical domain, of course, not the programming domain, since about 1930 or so. Many mathematicians have studied this, including Church, Tarski, Gödel, lots of people in Poland, in Germany, in England, and in the United States. It took a very long time, about 50 years, between 1930 and 1980, between the beginning of this activity when this was first formulated as logic with these particular rules, and the time when the Curry-Howard correspondence was realized or was discovered. At that time, it became clear that these things have a direct bearing on functional programming, actually helping people to write code. Because if you know how to prove things here, you just directly write the code. The first important thing that I need to say here is that there is an algorithm for deciding this question. So, in other words, this is called constructive propositional logic. It has a decision algorithm. An algorithm that takes any such expression, like this, however complicated. It can have tuples, it can have disjunctions, it can have implications, nested in any way whatsoever. It can have the unit, or nothing, or whatever, nested in whatever way. And there's an algorithm that takes this expression, assuming that all the types, variables here, a, b, and so on, are universally quantified. So that is always the case, so let's say. So for that case, there's an algorithm that decides whether this can be proved, whether this is a valid formula or can be proved. And at the same time, if it can be proved, what is the code that implements this function? This algorithm is constructive. It is not just proving that this can be derived. It actually gives you the code that implements this function. So this algorithm doesn't have a name per se, but it has been developed by a number of people, and there are many such many alternatives for this algorithm. I'll give you some links later, but for now it's important to say that this question is decidable. So there's an algorithm that answers this question, whether this can be implemented, and if so, how, what is the code. And I have started implementing this algorithm in a library called Curry-Howard. So I have a link here to this library. I'm not going to look at this right now. We're going to look at this a little later, after we have seen more examples. So one other thing that follows from the Curry-Howard correspondence is the curious resemblance with arithmetic, not only with logic, but also with arithmetic. So notice that I have chosen the symbols plus and product here. This was intentional. The logical symbols, which are the disjunction and the conjunction, do not have the same properties as the arithmetic operations of addition and multiplication. They do have properties that look similar. So here are some standard identities in logic. For example, A and 1 is A. A and B is equal to B and A, and so on. There are some identities like this: associativity of conjunction, associativity of disjunction, distributivity of conjunction, distributivity of disjunction, and then some other properties that have to do with implication. These are all theorems in logic. This you can prove, and the equal sign here can be read as double implication. So from x follows y, and from y follows x also. So both from x follows y and from y follows x. That is what the equal sign means in logic. Now, if you mentally replace here the disjunction symbol with a plus, what happens? Some of these identities remain true. So in other words, you move from logic to arithmetic. And then you ask, what are still the true identities? Well, most of them are actually still true, except this one, for example. A plus 1 equal 1. That is certainly not true in arithmetic. Also, the distribution of disjunction is not true in arithmetic. So this would mean A plus B times C equals A plus B times A plus C. And that's obviously false in arithmetic. In arithmetic, only the distribution of conjunction or distribution of a product over the sum, that works, but not distribution of sum over product. But in logic, the conjunction and the disjunction are perfectly symmetric. If one is true, the other is also true. So whatever statement is a theorem for disjunction, the same statement is a theorem for conjunction, and vice versa. So logic, therefore, has slightly different properties than arithmetic. So you cannot just blindly use plus instead of disjunction. It will be misleading if I would write A plus 1 equals 1. That's confusing. Well, obviously in arithmetic this is not true. So then the natural question is, what is the actual correspondence here? Is it the correspondence with logic or with arithmetic? And this is the question we will explore next. It turns out that both correspondence with logic and with arithmetic are useful. So these are kind of two sides of the Curry-Howard correspondence. The arithmetic correspondence is useful for certain things, and the logic correspondence for other things. So let me maybe comment a little bit on these identities. So what are these identities? If we take, say, this one, the first identity. Each identity, as I said, is just notation for two implications, one going from left to right, one going from right to left. Now, these implications correspond to code that has a function going from here to here, and a function going from here to here. So what do these two functions do? They convert values between the types. So there are two functions going in the opposite directions between two types. What do they do? So the interesting question is, can we somehow convert one type into the other and back without any loss of information? If so, then the types would be equivalent. We can encode the same information in both types. So then a natural question is, do these identities mean equivalence of types? So equivalence of types in the mathematical language is called an isomorphism. And the formal definition is that you need to have two functions, one going from A to B and one going from B to A, such that the composition of these functions in both directions is equal to the identity function. And if this is so, if you can find such two functions, then the types A and B are isomorphic or equivalent, which is the same thing. And the interpretation of this is that the values of these types can be encoded in the other types. So there's a one-to-one correspondence between the sets of values of these types. So whatever information you have that is in the value of this type can be encoded one-to-one with no loss of information by this type, and then vice versa. And so the functions f and g provide the recoding, the different packaging of the same information from A into B and from B back into A. And so when you do the composition of these functions, then the information is repackaged and then repackaged back, and it's the same information, so the value must actually remain the same after you do this round trip. And let's take the first example. This is the type. Let's ask, is this an isomorphism of types, or are these two types equivalent? So I will use this symbol, the triple equals, triple bar, or triple line, to signify that the types are equivalent. And they're not necessarily equal, they're equivalent, so there is an isomorphism. In Scala, these types correspond to a tuple of A and unit, and to A, type A, respectively. So if we want to demonstrate that these are equivalent, we need to build two functions. Let's call them f1 and f2 in the code. The functions have these types. So the first function has the type from a tuple of A unit to A. The second function is type from A to the tuple of A unit. Notice the double parentheses. So there's a parentheses around the tuple and extra parentheses here around the arguments of functions. So in Scala, the syntax is such that if you have a tuple as an argument, then you need double parentheses in the function type. Here, actually, the double parentheses are not necessary, because this is not an argument of the function. This is the final result type of the function. I wrote these parentheses here nevertheless, but they're really not necessary. I should delete them from the slides. So coming back to our question of isomorphism, we need to implement these two functions and check that their composition in both directions is identity function. Here is the Scala code. Well, the Scala code is very simple. You take a tuple of A and unit. You want to produce A. Well, you just take a pattern match on the tuple. You get the A as a pattern variable out of it, and you return the A. The second function is also very simple. You take an A and you produce a tuple. First part of the tuple is A. The second part of the tuple is the unit value. So, does the composition equal identity? Well, it should, because we take this A, we put it into the A type, and then we take that A and put it back into the first part of the tuple where it came from initially. So taking the tuple, going to A, going back to the tuple gives you again the same tuple, and vice versa. Getting an A into a tuple and then stripping away the second part of the tuple again gives you the same A. So it's kind of obvious that both directions of the composition give identity functions. Let us look at test code that implements this. So these are the two functions. I have deleted the code so that I can write it here again. So how would I write this code? Well, I look at the argument of the function. It's a tuple. So a natural way of write a function whose argument is a tuple is to do a pattern match. So I do curly braces because pattern match is a case expression and it requires curly braces in the Scala syntax. And then I say there's a and B as a pattern because it's a tuple with two parts. So I have two, let's see, the type of A is capital A, the type of B is unit. So then I can return. So what do I need to return? The value must be of type A. Well, I have only one. Oops. I have only one of a thing of type A. So that's it. The second one is even easier. So I get A, which is the function. Sorry, the argument of the function. And I'm supposed to return a function of this type. So I return an expression. I don't need parentheses because it's so simple. I don't need a case expression here, so I don't need curly braces either. So I just take argument A and return a tuple of A and the unit value. And the unit value is empty tuple, just this. This is the unit value. I'm done. So let me run this test. But before I run this test, or rather while I run this test, I want to show you this the way of verifying that something is a identity function. Let's say, how do we verify that? We have to do this in some clever way. The way I chose to do it is that I use a library called Scala Check, which allows you to check properties in a randomized way. So I can check that the composition of two functions, here's what I do. I say, for all integer n, it must be that the composition of f1 of f2 of n should equal n. So this should equal is a special syntax of the library, and for all is a function defined in the library. Of course, it's not going to go over all integers here. It's going to take some randomly selected integers. But that's pretty much as good as it gets in terms of checking such functions. And the second test is that I say for all x of type string unit, I have extra parentheses here which are not necessary. So for all x of type string unit, f2 of f1 of x should equal x. So this is the opposite direction of the composition of the two isomorphisms. So if both of these are correct, then indeed f1 and f2 are the two isomorphisms that we require to prove that this is so. So this is how we write test code to check the properties and prove that laws or equalities hold. Note that I put specific types here, integer and string. So this is true for all types. I just checked some specific types. That's good enough. These functions don't do anything with values. They just repackage them in some way, and so whatever that type is going to not going to matter. I just, to make sure that it works with different types, I choose some randomly some types, specific types, integer and string. The second example is I'd like to see if this is a type isomorphism. Remember, we had this formula in the logic. Disjunction of a and 1 is equal to 1. So a or true is true. Is this a type isomorphism if we translate that from logic into types? So that will become a plus 1 equals 1. Right? So the logical formula is valid. But is the type formula giving us a type isomorphism or not? The fact is that it does not. So these two types in Scala are the option type, which is disjunction of a and unit, and unit type. Obviously, these types are not equivalent. The information in an option type may be a value of type A, but the unit type cannot possibly represent any values of type A or anything non-trivial. A unit type only has one value, which is the empty tuple. So clearly these types cannot be equivalent. How can we see that in code, that they're not equivalent? And what is the significance of the fact that the logic formula is a valid theorem? Here is code that we can try to use to falsify this example. So I will write this code live, just again to show you how these things look in actual code. So we're supposed to make a function that takes an argument of type either of a and unit. So we should start curly braces, perhaps, and have something like, or right now we don't need a case expression, so let's say this is either a unit, this is EAU, going to something. So that's our function. We'll take this as an argument, and we'll return unit. Well, that's good enough, right? We just return unit. You're done. And actually, this is never used. So in Scala, arguments that are not used can be replaced with the underscore symbol, which makes the code kind of a bit cryptic looking, but this is a very frequent usage, and also you clearly say that you're not going to use this argument. Let's take the second function. So we get the unit. Yeah, well, actually, let me just go back. There's nothing else I could have written here. There's no way that I can use this value somehow to produce this. Empty tuple is empty tuple, it's empty. There's no way I can put something in it. So I could have a very complicated value here, doesn't help. The only thing I can do is to return the empty tuple. Here, I'm given an empty tuple. So let's say this is this u. And I'm supposed to produce a value of type either of a and unit. So how can I do this? Well, there are two possibilities in either, a left and a right. Well, I can produce some left of a, or I can produce a right of unit. Now, what would be a left of a? I need some a to get a left of a. So I could say left of some a, but what is this a? Actually, I don't have any values of type a. So I cannot possibly produce a left part of the disjunction. I must produce the right part, and the right part has the unit value. And there's only one unit value I can take anyway. So I can put this u in here if I feel like I'm very fancy. But this u is actually unit. So this actually could be replaced with this. There's only one value of type unit. I don't need to take it from the argument. It's going to be the same anyway. So this is exactly the same. All right. So now I have implemented these functions, and there's only one way of doing this. So the thing is, this test is going to, the identity test is going to fail. And I write this as a test that specifies that there exists some value of type v, which is, sorry, some value v of type either of integer unit, such that f2 of f1 of v is not equal to v. So if this, however, f1 of f2 of u should equal u. So in one direction the composition works, and there's only one value to check anyway. But in the other direction, the composition fails to work. So there are some non-trivial values of integer, let's say, in the left. And this integer is going to be transformed into unit, and then back it's going to be transformed into the right. And that's not the same as what it was before. So we lost information here. We had left, and then we lost it, and then we cannot recover. So this test is how it works, how it's shown. So we find that some logic identities give isomorphisms and some don't. So what does it mean? Well, logic identity, it just means that there exist these two functions, f1 and f2. They can be implemented. That's all it says. It doesn't say that, right? Because this is what the logical proposition means. It's the very foundation of the Curry-Howard correspondence. Logical proposition means we can compute a value of this type in the code. No more and no less. We can compute some value. Whether this value is useful or not is not clear. But we can compute a value. That's what this logical theorem says. Yes, we can write two functions that map option A to unit and unit to option A, or either. Actually, more precisely, this should be an either of A and unit. Option A is equivalent to either of A and unit. So yes, we can compute, we can write these functions, we can implement functions of these types, but the composition of these functions is not identity function. These functions lose information, or at least one of them loses information. And so for this reason, the types are not equivalent. So heuristically, types are not equivalent when they lose information. sorry, when the functions that you write to map the types into each other lose information. That is the intuition that we are gaining so far. So every time we implemented a function that does not lose information, like this one, we got A, we put it back. We got A, we put it back. So no information is lost. In the example here, we got something, we ignore it. We got something, we ignore it. In this case, it's okay to ignore unit because unit only has one value. In this case, not okay. In this case, we are ignoring possibly a value of type A. So that function loses information. So I put this in quotes because this is just intuition. This is not something we compute. The amount of information in the function, this is not something we compute. But this is the intuition I'm building about the functions. Here are some more examples of verifying type equivalence. The way to verify type equivalence is to try implementing the functions that go from one type to the other and back. So let me go through these examples. Example 3. We have a function that takes a tuple of nested shape. So there's a tuple of AB, and that tuple is inside a tuple of that and C. So this is how we write this in Scala. And we need an extra pair of parentheses because this is the argument of a function. So this is then a function type. The result is a tuple of this shape. We don't need extra parentheses because this is not an argument of a function, this is the result. How do we implement this function? Since the argument is a tuple, it is natural to do a case match. So we write pattern variables, let's say x, y, z, like this. You can write any names. Let me just check the types. Control-Shift-P. Type A, type B, type C. I'm supposed to return a tuple of this shape. Well, this is quite obvious. I'm done. Similarly here, let me just copy this code over to make things quicker. I'm supposed to, now listen, notice it tells me that the type is wrong. Well, of course it's wrong. I haven't finished writing the code. Now I'm finished. How do I test that these functions are correct? I write the for all, then for all what? For all values q of this type, so I choose specific types for A, B, and C. I must choose specific types. There's no way to check with values of type A. There's no such thing. I need to use a specific type when checking and when using this function on actual data, of course. And then I say this should equal this. So for any q, f2 of f1 of q should equal q. So which means f2 composition with f1 or f1 composition with f2 is identity function. And similarly for the other direction, f1 of f2, I put the tuples in the opposite order. Notice again, I have to put extra parentheses around the argument of the function. This is the Scala syntax. If I put types, so for types I need extra parentheses. For simple functions like this, I don't need extra parentheses because I don't have to say types. Types are specified on the left and I don't have to specify them on the right. But here, when I do for all, the types are free, not specified anywhere, and then I have to specify the type for the function argument in Scala. and then I have to put the extra parentheses around it. Just an aside about syntax. Example 4. This is a theorem of logic. If you interpret plus as disjunction and times as conjunction, it's also a theorem of arithmetic. Just like this one, by the way, was also a theorem of both logic and arithmetic, interpreting our notation that way. So how do we check that this is true? The two functions must have this type. The first function is a tuple, argument is a tuple of two parts. One part is either of a, b, and the other part is c. The result of this function is an either of left part of the disjunction being a tuple of AC, the right part of the disjunction being a tuple of BC. And the function f2 has the two types in the opposite order. Note extra pair of parentheses around the tuple on the left side. So how do we check that this is true? We need to write this code. So how do we write this code? Well, since the argument of this function is a tuple, we need to do a case match. So let's say this is either a, b, and c. What is the type of this? Yeah, either a, b. Type of this is c. I'm always checking. I always check these types when I do a case match, because if you make a mistake, it might still compile, and case matches are less strictly checked in some cases. Not in all cases, but in some cases. Just to be sure, I use IntelliJ to check all the types in the case match. Now, either a, b is an either, so I need to figure out in which part of the disjunction I actually have a value. So this could be either a or b. So I need to match on EAB. So I say EAB match, and I open braces because it's going to be again a case expression, so I need braces. Case clauses expected. Yes, of course, I also expect them. Now there's this symbol which I use to generate the clauses. That's convenient, especially if you have many clauses. Now the name of this thing is inconvenient. I'd like to make it A and B because that's much more suggestive. So there are two cases in either. There could be a left of A or a right of B. If we are in A, now what do we do? We need to return an either of AC or BC. So what do we have here? We have a C and we have an A. Well, clearly we can return an AC. And that will be in the left part of the disjunction. So I return left of a tuple AC. If I'm in the right here, then I have a B and also I have a C. I don't have an A. You see, I remind you that the case expression is such that these pattern variables are defined only within this scope. So if I'm here, I don't have A anymore. So the language prevents me from making this mistake of using A when I'm in the right part of the disjunction. Okay, so here I return a BC. Obviously I can return a BC because I have a B and I have a C. Now this is red because actually it wants to have an either of AC and BC, and so this BC must be in the right part of the disjunction. I need an extra parentheses because it's a tuple. Reformat this, I'm done. This function, let me do the same thing again. Now this is an either, So I'm going to say either AC or BC goes to what? Well, it goes to something. I need to match on it right away because there's nothing else I can do. I don't know if I'm here or here, in the left or in the right part of the disjunction. If the value I'm given is a tuple AC in the left, or it is a tuple BC in the right part of the disjunction. So let me do that. EACBC match. And then I have the same case clauses I generate. And then let me rename these variables as AC and this as BC. Because this will have type AC and this will have type BC. Now, apart from the red, because, well, the red I haven't finished writing, there's a yellow. What is this yellow? We'll see it when I get rid of the red. Right now, apparently, the red is more important for IntelliJ. I always look at what's yellow. It's often very helpful. Almost always. Okay, I'm in the AC, so there is a further possibility. No, there is not. AC is a tuple, so it's not a disjunction, it's a conjunction or a product type. So I have A and I have C. What am I required to produce? A tuple of either a B or an C. Well, I have a C. Obviously, I can produce that in the second part of the tuple. The first part of the tuple needs to be an either of A, B. So I have an A. Sorry, I should have said first I have this A and C of type tuple AC. Let me decompose the tuple like this. So this syntax says I'm introducing new variables A and C and decompose the tuple into them. Or I could have just put these variables right here. Save me a line of code. All right. Now, what is the first thing? It's an either of A, B. Well, I have an A, so that's going to be in the left part of the either. And I do the similar thing here. I have a right B and C, and I put a BC tuple right into the pattern. Now, notice the pattern can be nested. It doesn't have to be so simple. It can be a right and then further destructuring or specification of structure of the pattern can be given. So that makes code easier to read and easier to write. Okay, let's look at what's yellow now. The first thing that's yellow, convert match statement to pattern matching anonymous function. Okay. There's this symbol here, which I click, convert. Huh. The code became much shorter. So actually, this syntax is already a function that matches its argument with these cases. And the argument is of this type. So I don't have to say x arrow x match. That's just not necessary to write at all. A very common pattern, and it just makes code shorter. What is this yellow on A, actually? Suspicious shadowing. Now we know what that means. It means somebody already defined a variable A outside of this code, and now we introduce a pattern variable also called A in the case expression. And that shadows the A that somebody already defined outside of this code. Well, I didn't define any A's that are visible. All my A's are these internal variables. They're not visible outside. Who defined this A? Well, actually, it's the test library that defined the A. So I'm not going to be able to get rid of it, since I'm using the test library in order to perform the testing and run the code. I'm not going to be able to get rid of this yellow. But in ordinary code, I won't be inside the test, and so this A would not be yellow in ordinary code. All right, so I'm done. So this actually works. Let me run this test. So I implemented the two functions, and then I check that the two directions of their composition take arbitrary values of this type and return the same values, and take arbitrary values of that type and return those values. So that's the way that this is going to be tested. Tests pass. The next example is this one. A slightly more complicated thing. A disjunction as an argument, so argument of the function is disjunction, the same as a tuple of two functions. Let me look at how that works. So here I already wrote all the code, but the way to write this code is exactly the same as I was showing you previously. You just go step by step and figure out each part of the disjunction and so on. So let me go through this code more quickly. The left hand side is this. So it's an either A, B as an argument going to C. So my function has a type, argument being this, either A, B going to C. That's the type of the argument of the function. And the result of the function is this, from A to C, from B to C. That's a tuple of two functions. So what do I do? Well, I take a P, which has type either A, B to C, and I return a tuple. Now, tuple consists of two functions, from A to C and from B to C. Now, from A, it takes an A, and then it applies. So what can we do with an A? Well, we can put this into here, pretending that we had an either with A on the left, and we put that as an argument into P, and we get a C out. So that's what this code says. P of left of A, and B goes to P of right of B. The function going back takes this as an argument, a tuple of two functions, and it needs to return this as a function. Now I remind you that parentheses around this function on the right are not necessary, because the arrow, the function arrow, is associative to the right. And so these parentheses are implicitly here. I don't have to put them. They don't change the meaning of the code. So I can say that I have now a match on the tuple, which is here. Then in this tuple, if I take the value of AC, that's a function from A to C, and then I also take the value BC, which is a function from B to C. So I decompose the tuple into two parts, and then I return this expression, which is, as I just showed, it's equivalent to a function of the sort x going to x match. So this syntax is the same, it's just shorter. Now what is this x? Well, this x is obviously this either AB here. And so we match on this either AB, and so this is, let me call this EAB to be more visual. So this matches on the value, and if it's in the left, then we get an A. We can apply this function to A and get a C out. If it's in the B, we can apply this function to B and get again a C out. So we get a C out in either case. Now the syntax becomes shorter, but somewhat more cryptic. So that's why I wanted to put this in for illustration purposes, but in most cases this won't be necessary to write. And the test shows that this works. The test is written like in a two for all, nested two for alls. So the first for all p, and we get a function, and then for all arguments of that function, we verify that this works. The thing is, these functions return functions. We cannot directly verify that functions are equal. We have to put, so if I want to verify that function A is function F is equal to function G, I have to put in all kinds of arguments into F, the same argument into G, and check that the results are the same. This is the only way to check that two functions are equal. Oh, clearly, I'm not going to put in all possible arguments. It's just impossible. So I'm going to just test with some randomly chosen set of arguments and hope that that's good enough and that will catch bugs if there are some bugs. So that is how this works. Example 6 is to show that this is not an equivalence. Now, this is actually a valid theorem in the logic. This is this theorem, distribution of disjunction, but it is not true in arithmetic, obviously. If you put a plus here, a plus bc is not equal to a plus b times a plus c. So rules do exactly the same thing. So this is an either of a and a tuple bc, and this is an either of ab tupled with either of ac. Now, if we look at the code to see how this is implemented, then what happens is that if you are, let's look at F2. If you are in the left here, but in the right here, so this is a tuple of two either values, so they can be independently chosen. This is on the left and this is on the right, let's say. So if you're in this situation, how can you return an either of A and a tuple BC? You couldn't have a B. You don't have a B. You're on the left, so you don't have a B. And here you have a C. So you have only an A and a C. If you have only an A and a C, there's no way for you to return this tuple. You don't have a B. So the only thing you can do is you can return this A in the left part of the either. And so the code returns the left A, and here also returns left A. And there's only one case when it returns a right of BC. It's when you have B here and C here. So clearly this code loses information. So if you're given A here on the left and C here on the right, you're ignoring this C. You're not returning it. You're returning a left of A. And so function F2 loses information in this sense. And sure enough, in the direction of F1 of F2, we have a violation of the identity requirement, but in the other direction it works. So this is not an isomorphism between the two types, but we can implement both functions f1 and f2. So just as in the other case, what we see is that the logical theorem guarantees that we can implement the two functions. We can implement from left to right and from right to left. Whereas these functions do not actually satisfy the isomorphism requirement, but logic cannot guarantee that. The arithmetic identity obviously does not hold, and we see that this function f2 loses information, and so it is not an equivalence of the two types. And the tests here are slightly more clever. So I have a function check that takes type parameters, and it runs this with type parameters. Then I can put any kind of types I want, just for fun, to check that this works. And the arbitrary thing here, I'm not going to talk about this much. This is something you have to do with this testing library. But Scala check is a very powerful library that allows you to check, to verify equations, properties, requirements, and laws of this kind. So we have seen a curious thing, that actually when the arithmetic law holds, also the types are equivalent. When the arithmetic law does not hold, then we lose information and types are not equivalent, even though the logical theorem holds. So how can we understand this? What is the relationship between the logic and the arithmetic side of the Curry-Howard correspondence? To understand this, consider the types that have finite sets of possible values. For example, Boolean type has only two possible values, true and false. Now, in the computer, most obviously integers have a finite set of values, a very large set, but a finite set. Floating point numbers also have a finite set of values. So pretty much everything in the computer falls into this class of types that have a finite set of possible values. It is convenient sometimes to think that integers are arbitrarily large, or strings are arbitrarily long, or arrays are arbitrarily long, but actually computers have finite memory, and so even it could be very large, but it's still finite, theoretically. So let's consider, therefore, without loss of generality, only the types that have finite sets of possible values. And let's compute how many values we have in the sum type or in the disjunction. And that's clearly going to be the sum of the numbers of the two types. So the size of a type, or cardinality of the set, to use the terminology from set theory, the cardinality of the set is the same as the size of the set. How many elements are in the set? So the size of the set of the disjunction type, a plus b, is equal to the sum of the sizes of the sets for a and for b. That is clear because we have a disjunction. On the left we have this many possibilities. On the right we have this many possibilities, and there's no possibility of having both. So there's no intersection here. It's a disjoint union or disjunction. The product type, or the tuple, obviously we can have any value of a paired with any value of b. And so there's an a times b possible values in this type. The function type provides the set of all maps between the two sets, a and b. And so it is the b to the power of a, because for each a, we can choose any b that corresponds to it. And so this is b multiplied by itself 8 times. And obviously then, if two types are equivalent, then they must have the same number of values, the same size of the sets. And if the set size is different, the types cannot be equivalent, because you cannot repackage all the possible values in the other type without losing information. And then come back and get the same value back. So because of this, whenever the identity that we had is a valid arithmetic identity, that has a chance of being an equivalence of types. And whenever it is not a valid arithmetic identity, like this one, for example, is not a valid arithmetic identity, there's no way in this case then that the types are equivalent. This is a valid arithmetic identity, so the type and the types are equivalent. So I'm not trying to prove here that any arithmetic identity will automatically give an equivalence of types, but this is highly suggestive. Pretty much any reasonable arithmetic identity of this sort, like a plus b equals b plus a, and so on, a plus 0 equals a. Any kind of reasonable arithmetic identity will give an equivalence of types. And certainly, if the arithmetic identity does not hold, there's no way that the types could be equivalent, because the cardinality of their value sets is different. Also note the curious identities that I listed here. These are identities related to powers. These are arithmetic identities. Each one of them gives rise to a type equivalence if you translate it according to this formula. So a to the power of c corresponds to the function from c to a, and this is the product, so that corresponds to a tuple. And so here, for example, we have this identity, which we verified in code. But this is c to the power a plus b equals c to the power a times c to the power b. Obviously an arithmetic identity, this one. So not only identities that have to do with multiplication and addition, but also powers, exponentiation, in other words, as arithmetic identity gives rise to equivalence of types. Logic identities do not always give rise to equivalence of types. What they give is that you have two functions, from one type to the other and from the other to the first. Now these functions guarantee that if you get a value of one type, you also can get a value of another type, and vice versa. In other words, if you can implement one type or compute a value of one type, then you can compute a value of another type. But it tells nothing about what values and how many different values you can compute. So logic identities give the equal implementability of two types. So if one is implementable, the other is implementable. Where here implementable is the same as you can write code to compute it, or you can write code to define that function. Because defining a function is the same as computing a function value. It's just different words for the same thing. Since in the functional programming, functions are values. So defining a function means you compute a value of function type. So to summarize, arithmetic and logic formulas have different significance, and the arithmetic formulas are related to type equivalence, and logic formulas are related to being able to implement types, being able to compute values of this type. So being able to implement at all is usually interesting for functions, but being able to say that one type is equivalent to another, that is usually interesting for data types because function types are never compared much, but nevertheless you can still treat functions as values, and all types are just types, and you can use the same reasoning about types, about functions and about data at the level of types. And so these are the two ways that the Curry-Howard correspondence gives us information about types. Arithmetic formulas with types tell us which types are equivalent. And that is important. If I'm trying to write my program, I need to know what types to use for data. And if one type is equivalent to another, I could use one or I could use another according to convenience. I know I can always repackage one to the other or back without any loss of information. And so I will understand how to choose those types more conveniently. I have more choices if I know which types are equivalent. For this, I use arithmetic reasoning. So I translate types into arithmetic formulas, and I reason with them pretty much like I reason about high school level algebra with polynomials and powers. I have identities like this. I have basically all identities of high school algebra completely translated into, well, I just showed them. These are some examples, and all others, all other identities out of here, for example, these are all valid as well as arithmetic identities. All these identities tell me how to design my types. So and this is what I mean when I say reasoning about types. This reasoning is specific answering of questions of what types to use in my program. And in order to find out, I can write down simple polynomial or power laws and simplify types, let's say, like I simplify expressions in algebra. So there are different kinds of expressions, such as exponential, polynomial, and so on in algebra. And the class of expressions that we have encountered so far are exponential polynomial expressions. That is, expressions made up of constants, like 1 as a constant, sums, products, and exponentials. Corresponding to this, in the functional programming, we have what I call exp-poly types, or exponential polynomial types. These are the primitive types, like integer, string, and so on. These correspond to various constants. Then there are type variables as well. So, and then there are disjunctions, tuples. So disjunctions corresponds to sums, tuples corresponds to products. So these are like either, option, case classes with seal trait. Tuples correspond to products, and functions correspond to exponentials. So function types correspond to exponentials, and so on. Now, in functional programming community currently, the terminology is that algebraic types are what I hear explained to be polynomial types. So types that have primitive types, disjunctions, and tuples, and usually not functions. So usually they're not called algebraic types. Now, the word algebra is used in so many different meanings and senses that I'd like to keep it very clear what exactly I'm talking about. And so I don't want to say algebraic types. I want to say more specifically polynomial types or exponential polynomial types. And if there are some other types, I'll have different words for them. So until now, we have not seen any other types except exponential polynomial types. And in fact, these are the only widely used kinds of types in functional programming. And here is an example of reasoning with types that I was talking about. or algebraic reasoning that I described. Here's two specific examples that I'm going to give right now. The first is to define a list of integers. So the type that represents a list of integers. So we'll define this from first principles. In previous tutorials, I have used the standard library of Scala with sequences and maps and all that. Now, those are defined in the standard library. I'm not going to write another standard library here, but it's important to see how types are defined and how recursive types like lists or arrays or sequences can be defined using polynomial types. So you just add recursion to the types and you find that you can do this. So consider this definition. So there's an integer list, int list. I'm defining a new type using the syntax with the sealed trait and case class. So there are two cases. One is empty, which is a case object, so it's an empty tuple. And the next one is non-empty, which has two parts. One is integer, and the other is int list. So it's referring to itself in the definition of the type. So in this sense, it is recursive. It's a recursive type. This is allowed, so that you can do this in Scala. The short notation for this type looks like this. Int list is defined as, or is equivalent to, 1. So this is the 1. Plus the product of integer and int list itself. So this definition is a recursive polynomial type, as I would call it. It's recursive in the sense that this type refers to itself in its own definition. Now you see the short notation is much clearer and very suggestive of various algebraic manipulations. Let us add a type parameter, so not just always using integers in the elements of the list, but let's do type A, any type A. So the short notation for that would be like this. Okay, we define exactly the same thing. Actually, there are different ways of defining this. One is like this. So we introduce a type parameter, and the case object extends this type parameter with nothing. So this is an example where we can use the type nothing. We don't actually have any values of type nothing, and because this is an empty tuple, basically. This is a named empty tuple. We could have actually said final case class, nil, and then empty parentheses. And that will be even more clear, even clearer, that we're just putting a name onto an empty tuple. And that extends list with type equal to nothing. And then we define this case class with this strange name, double colon. Well, this is kind of traditional in functional programming to use this name. This is also used in the Scala standard library, but the double colon is just a name. You could call this anything. You could call this ZZZ if you want. So it has, again, exactly the same structure as this list, except that it's using the type parameter now for the value instead of int, and it refers to list of A recursively, extending list of A. The short notation for this thing is this. Now, we know the laws for the types, and the equivalence corresponds to algebraic manipulations like in arithmetic. So let's perform that kind of manipulation. So list of A is 1 plus A times list of A. So let's say 1 plus A times open parentheses, 1 plus a times, open parentheses, 1 plus a times, and so on. Let's now use the arithmetic identities. We know that they correspond to type equivalence or isomorphism. And we can expand this and we get an expression which looks like this. It's an infinite disjunction of empty list, list of one element, list of two elements, list of three elements, and so on. Of course, this expression doesn't really mean much. It's an infinite disjunction. It's not well defined. We should stop it at some point, putting a list A at the end in some way. So at last, we can only do this a finite number of times. So this triple period, it should only be used a finite number of times. So the last term would be A times A times A times list A. And that would be well defined then. It will be a well-defined equivalence of types. But this is very suggestive. This is basically showing you that this recursive definition gives you an infinite disjunction. It gives you a possibility of having a list of any length. Very visually clear what this type is doing. And there's a curious analogy with calculus. So imagine you have a function list of t, and this function satisfies an equation of this sort. So I'm replacing a with a real number here to have an analogy with calculus. We can solve this equation, and we have list of t equals to 1 divided by 1 minus t, and we can expand this in a series, and we get a very much the same expression as this, an infinite sum of all the powers of t. So this is just an analogy. It is not directly useful for functional programming, because there's no way for functional programming to make sense of dividing 1 by 1 minus t. There's no minus as far as we have seen. But it's a curious, fun analogy. And even derivatives have an analogy in functional programming. But I will not talk about this right now. Let's go through some worked examples to kind of repeat what we have seen in this tutorial and get a bit more experience solving various problems using the Curry-Howard correspondence and reasoning about types. The first example is we want to convert a type notation into Scala code. So this is something that we should be able to do. We should be able to convert in both directions. Take Scala code and write the short type notation, which is much easier to reason about when you have to answer questions about types, such as, am I using the right type for something? Do my functions need to be so complicated? Can I simplify the type maybe? So before even you write code, you should ask such questions and write down the types. Whenever you see that the type gets very complicated, reasoning about types is much easier in a short notation than in the code notation. So for this reason, it is useful to be able to go between the short notation and the code in both directions. So let's see how we can define, suppose some reasoning gave us this type in the short notation. What is the definition of this in Scala code? Here is my implementation. So I define the type. It's easier to define the type like this. I could have defined a case class with a single value in it, but then I would have to define an extra name. Because if I define a type, there's just one name here, my t. The case class would look like this. and then I have to say name, like f boolean going to my t vals of t. So I would have to write all this, and I would have to invent another name. If this is useful, do that. Otherwise, do that. Otherwise, just put a type. Type alias, as it is called, or type name, named type, and it can have a type parameter. I'm required to implement a disjunction, so I need to define this auxiliary class or type. The disjunction is this one, so 1 t integer times t and function string to t. Therefore, I have 4 cases. One is the empty, so that represents the unit type, empty tuple. I call this empty value t. Then there's a single value t, then there's a t with integer, and then there's a function string to t. So each of them has a name, so I just chose names for describing what these things do, but in a real application, these will be names that mean something more interesting to the programmer. And that's it. So every time I put a type parameter on the case class, and I say it extends the trait with that type parameter. How do I declare values of this type? Well, I just do it like this. Since there is no name on the case class field here, I don't need to put a name here. I just say b goes to this, and that becomes that type. Here I give an example of some interesting function from Boolean to this. So if the Boolean is true, then I return this case. And if the Boolean is false, I return the empty value. It's up to me what I do here, but basically I can do that. So that for integers, I need to return here a function from string to integer, and I put this function, which returns the length of the string, into the case class with this name. So this is how I use the definition I just gave. The second example is to transform this type into an equivalent sum type. So sum types and disjunctions are the same thing. This type is a tuple, the tuple of 2 ethers. And I want to transform this into an equivalent sum type. So the first thing I do is I write this type in the short notation. So the short notation for this type is this. So I use the star for the product, which is even more suggestive of the arithmetic correspondence to types. And then to convert this to a simple disjunction, I simply expand the brackets, as in school-level algebra. And the result is this sum, or disjunction. So it means that if my first type, T1, is a tuple of 2 ethers, my second type has to be declared as a disjunction of 4 parts. So I declare a sealed trait with 4 case classes. Each of them must have all the 4 type parameters. And you see it becomes quite verbose. I have to say each time I have to repeat these 4 parameters, these 4. I have to say extends T2 blah blah every time. And I have to say final case class every time. So this is the verbosity of definition of disjunction. However, once this is done, the code is not verbose. So this is, so I defined 4 cases. T2 has T2AC, T2AD, T2BC, and T2BD. And each of them has 2 parts in the tuple, in the case class, or named tuple. So the 2 parts are of the types that I'm supposed to have. So for example, A and C, A and D, and so on. So once I have defined these types, how do I specify their equivalence? So I know that this type is equivalent to this one because I just expanded the brackets in the algebraic polynomial expression. And I know that such operations always give type equivalences. But in a particular code, one part of the program might give me a value of T1, and another part of the program might require a value of T2. So they're equivalent, but I need to transfer one into the other. So I need these functions, let's call them F1 and F2 again, that repackage T1 into T2 and vice versa. So let's write a code for these functions. So T1 goes into T2. How do we do that? Well, T1 is a tuple of 2 ethers. So to write a function that takes a tuple as an argument, I started with a case match, and I match the tuple directly with the 2 arguments. Now each of these arguments is an ether, so I match AB, and I have a case left and a case right. Case left of A, case right of B. And in each case, I also need to match CD, which is this second ether. So I have these 4 combinations. I first match A, and then I match C, and then I match, or D. And then if I match B, then I also could have matched C or D. And each time I return the case class instance that corresponds to that choice. There's nothing else I can write here in this function, really. I'm just repackaging the data in from this format into this format. And this entire code, in fact, could have been generated automatically. I'm writing a library to do that. It's not ready yet, but this code is unique. There's only one way of writing it correctly. It follows from the type, from this type expression, algorithmically follows. So it can be derived automatically by a library. However, let's not jump ahead. The function that converts T2 into T1 is easier. T2 is a case class. Sorry, T2 is a sealed trait with 4 case classes. So we directly match on T2 with 4 cases. Note again this short syntax. So I'm not writing this because that is not necessary to write. So I have 4 cases, and in each case I directly return the tuple of 2 ether values that I'm supposed to return. So if I have, for example, A and let's say A and D, or B and C, then I return right of B, left of C, or right of B, right of D, and so on. And I check that this works. Next example is to show that A plus A and equal A and 8 times A equal A are not type equivalences, although they hold in logic. So these are logical theorems. that are valid in logic, but of course as arithmetic statements these are wrong. A plus A is not equal to A for any A, and so A times A is also not equal to A for any A in arithmetic. And so we expect that these are going to be two pairs of functions that we can implement, going from this to this and back, but these functions will not compose to an identity. Let's see if this is so. Implementing the function that goes from either to A is very easy. We match on the either. We have a left of A, we return A. Have a right of A, we return A. Going back is even easier. We take an A, and now we need to return an either. So which one do we return? We return left or right? We must choose either right or left. Now, there's no information in the A, in the argument. There's no information to tell us what to choose. So this choice has to be hard-coded here. It has to be chosen once and for all A. That's actually the problem, because the other type has two versions of A, left and right. And here we lost that information. And so coming back, we have to choose one of them. Now, I would like to emphasize that this is not a political choice here between right and left. It has nothing to do with politics. And the names right and left were chosen simply because it's the left side of the disjunction or the right side of the disjunction. So whatever we choose here, we cannot satisfy identity. So this function f1 already has lost the information, and if initially we had the left part of the disjunction, we project it onto A, and then we go back to the right part of the disjunction, so we do not recover the initial value, which was the left of A. And that is the code that shows that there exists some value that does not satisfy the law of identity. To show that the product of A and A is not equivalent to A, then we do a very similar thing. So this function is take a tuple of AA and return A. So here again, we can return the first part of the tuple, or we can return the second part of the tuple, but we have to choose which, and we have to choose in the same way for all arguments. There's no information here that can guide us to choose the left or the right part of the tuple, the first or the second part of the tuple. So let's say we choose the first part of the tuple, and then we lose the information in the second part. And that's the information loss that our intuition tells us this cannot be a type equivalence. And indeed it is not. So the function going from A to a tuple of AA, it can only do one thing. It can duplicate the value A into a tuple. And so obviously we cannot recover information from the initial tuple. We lost the second one, and then we duplicate. So let's say the tuple 1, 2 will be converted here to 1, and then converted to 1, 1. So that's obviously not identity. Show that this is not a theorem in logic. Now, this means we are not able to implement one of the two directions. Right? So logical equivalence means that we have from like logical x equivalent to y, x equal y means we have x to y and we have y to x. So in code we should be able to implement. Now if this does not hold in logic, then we should not be able to implement one of these directions. Let's see how that works. So we're trying to implement this. We have a function from a, b to c, and we need to return a function, either a function from a to c or a function of b to c. So how can we do that? Well, we have to, so let's write this, actually, let's write this function in a slightly different syntax. It's probably a little confusing, but no, let me rewrite this into the syntax we've been using until now. But this is a completely equivalent syntax. A function, type parameters, and then argument, colon, result type. This is a standard way usually in which the Scala programs are written. But in this tutorial, for clarity, I want to emphasize the types of everything. And so in this notation, types are not so obvious. So let me write it in the way that we've been doing. So we just say the type is this going to that. And then we have FABC is the argument here. There's somewhere an extra. Yes, that's it. So yeah, so we take this as an argument, which is this function from a, b to c, and we're supposed to produce this either value. Now, we need to decide whether we produce a left or a right, because there's no information on the left here, or in the argument, to tell us which to choose. So let's suppose we decide the left this time. So we return the left of this. So now we return a function that takes a and it needs to return c. Now how do we return c? To produce a value of type c, the only way for us is to use this function fabc, which produces a c given a pair of ab. But we don't have ab, we have only a. We need to do fabc of a comma something of type b, and we don't have that. So we cannot implement this function. This is the usual way in which we can see that some function cannot be implemented due to its type. Is that we're supposed to produce a value of some type, but there's no value of that type. Nobody can give us that value, and our arguments are not enough. We're not given enough data to produce that value. So then, obviously, this is a no-go. In the other direction, it works. If we have an either, it's a left or a right. If it's a left, we have a function from a to c. We can take this tuple of ab, take the first element of it, which is a, put into that function, and we get a c. So that works. The second works in the same way, the second case. So one direction of the logical inference works, logical implication works, but the other does not. So f1 does not work. That is how we cannot implement a function f1 of this type. And this is what it means that this statement is not true in logic. Next example. Now, these examples from now on are more realistic. So we will use the skills that we learned, and we'll see how it works with these functions that are more useful in real programming. So let us denote this type, reader, simply like this. It's a function. We are required to implement functions with these types. A goes into reader EA, and reader EA to AB to reader EB. So we define a type reader like this, and these two functions, let's call them pure and map. So pure takes A and returns reader EA. Well, reader EA is just E to A. So it takes A. So we return a function that takes A and returns a function that takes E and returns A. Now we have this A, we don't use the E. That's the only way to do this. So this is a function we've seen before that ignores its second argument and returns the first one. The only difference here is that I'm using the type constructor. So I remind you that this thing is called a type constructor because this is similar to something that constructs a type given some type variables or some type parameters. It's quite similar to a function at type level. So a function that takes types and returns other types. And this function we define like this. So type level functions. You can think about them in this way. They can have several arguments and they return expressions that are types, type expressions. Just like functions that take values return expressions that are values, type level functions take types as parameters and return type expressions. So these are type constructors. Let's look at the map function. So we take reader EA, AB, and we need to return reader EB. So how do we do that? So let's say R is this reader EA. We need to return a function. So I remind you, this is the right associativity of implications. So this is in parentheses, what I just highlighted. So we need to take this reader EA and return a function. Let's write the code for this. Then we take a reader EA and return a function. What is that function? That function takes A to B. Let's call this F of type A to B. So IntelliJ knows. And it returns reader EB. Now what is a reader EB? Is a function that takes E and returns B. Right? So let's take E and we need to return some B of type B. So how can we get a value of type B? The only way is to apply this function to something of type A. So let's call it like that. Let's say f of A, where A is some value of type A. How do we get the value of type A? Well, we're given R, which is of type E to A, and we have an E. So we can apply this R to this E. We get a value of type A. We apply F to that A, we get a B, and that's our final result. So now all of this seems to be very long-winded. So let me write a different syntax, which is shorter. Call it map1. Instead of writing the types like this, I will put each of these arguments right next to the function name. This is just a different syntax. I still need extra parentheses for each argument here. Remind you that Scala needs parentheses around type arguments, around types of arguments of functions. So f is this, so I write exactly the same function in a different syntax. Instead of this, I put a colon, because this is the final result type. and then I just write this. Very simple code, because E, so you see this R is now here, this F is now here, this E is here, and then I have inlined everything. F of R of E, that's all. So this is the entire code. Now, there's only one way to write this code. The types are such that there's no freedom. There's only one way to get a value of B. There's only one way to get a value of A. And so there is an algorithm that I mentioned before that takes a type expression and produces the code. I started to implement this algorithm in a library, and I can already in this library at this early stage, I already implemented the part of the algorithm that deals with function types and tuples. Not yet in every situation, but function types in every situation, tuples in some situations. So I'm still working on this. Eventually I will implement entire algorithm. And right now the library can already derive this function, because it has nothing but implications. The next example is show that one cannot implement this function. Now, what is this function? This would be very similar to map, except with respect to the first argument, not to the second. So this is a map with respect to the second argument. We map A with a function A to B into a B. Now, if we want to map the first argument, this cannot be done. And the reason is that we have an R, which is a reader of AT, which is a function A to T. And we have A to B, and we need a function from B to T. So how do we produce a function of B to T? We take B, we need to produce a T. But we don't have a T unless we have an A. Right? This is a function from A to T. How can we get an A? Well, we can't get an A. We cannot. We cannot take a function f and produce an A out of it, because function f consumes an A. It does not produce an A. So this is a no-go. It's exactly the situation when you're required to produce a type, but you're not given any means of computing the value of that type. However, if we were to reverse this direction, then we can implement this. Because now we have a B, we can use this function to get an A, and that will solve our problem here. We needed an A. We can get that A from an F, which is of type B to A now. So this works. In other words, it's like a map, but with this arrow reversed. And this is called a contra map. So this is a contrary motion, so to speak. So it's just an example showing you that some types can be implemented, other types cannot be implemented. Next example is to implement this function. So it's a map on the type 1 plus A. When 1 plus A is option of A. We know that option has a map, but that's in a standard library. Let's try to implement it ourselves. And our idea is that we should avoid information loss. Now, what would there be as information loss? The thing is that the option type has two cases, none and some B, let's say. If we have a function that returns an option, we can always return this part of the disjunction, because this is always available. This is the true part that is empty and empty tuple or unit type, we can always return it. So we can always implement a function that ignores its arguments and returns unit. Or in the case of option type, this is called none. All right, so this is a named unit, but in the language of types, this is just one unit type. But this kind of implementation that ignores its arguments and always returns unit loses information. So in order to fix that and require that information is not lost, we need some criterion that shows what is that information that needs to be not lost. So let's make a criterion that if we put some option value in here, and if you put an identity function in here, so a function that certainly does not lose any information, then I should get the same option back as I put there. So this would be my criterion for not losing information. Let's see how this is done. So we can get an option and a function f from a to b. So now I'm writing this in the syntax with arguments here, because it's slightly less typing, but also the types are a little obscured. However, this is a good exercise to go between the short notation, which is this, and a function type in Scala, which is this, declaration of a function. So this is what represents the short notation here. Since my argument is an option, I need to match on it. So it's a disjunction. Option is a disjunction with two cases, some A and none. I have to match on it. If I have some value in there, then I return non-empty option with transformed value. There's no other way I can do it. I need a value of type B. The only way I get a value of type B is when I apply f to some value of type A. There's no other B given here anywhere. So I must apply f to A. So that's what I do. In the case of none, there's nothing else to do except return none, because there's no way to find the value of B from nothing, or a value of A from nothing. The other possibility would be to always return none. So this is what I described before as the information loss option. And now if I check this, the test will check that if I use the map, then there is no information loss, so identity is always preserved. And if I use the bad one, then there is some value of initial x, so that the value is not preserved. And then I check it with integer type. So that's this test. And let's now implement map and flat map in the same way for the either type. Now, for the either type, usually one prefers R over L. I will show you what that means, one prefers, because there is a choice in implementing map and flat map for the either type. For the option type, there is no such choice due to this criterion, but for the either type, information loss is not a problem. The problem is that there are two sides, and let me show you what that is. So I need to map. I have an argument which is an either of LR, a function from R to T, and I need to return an either of LT. So I match on the either, and if I have a right, then I apply the function f and I map on the right. But if I have a left, then I have a value L. I cannot transform L with this function. So I have to return it unmodified. So this is what it means to prefer the right. It means that the type is given such that it is the right one that is being transformed, and the left one is not being transformed. And I could, of course, put here a different type, like L to T instead of R to T, and then I would have to put the left transformation. Now let's look at flat map. The typical signature of flat map, let me remind you what flat map is. It's the first time we look at it in this tutorial. So if I have a sequence and I'm mapping with x going to sequence of x, 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 let's say, the result of this would be a sequence of sequences. It will be a sequence of sequence 1, 1, 1, comma, sequence 2, 2, 2, comma, sequence 3, 3, 3. And then I do flatten. And that gives me a flat, not nested sequence, 1, 1, 1, 2, 2, 2, 3, 3, 3. And the combination of map and flatten is shortened to a function called flat map. So what is this type of flat map? So flat map takes a sequence of t, so something of type sequence of t. Then I say dot flat map, so this is actually implicitly one argument of flat map because I'm putting a dot here, so in an object-oriented syntax. And then I have a function from t to sequence of possibly, well, let's say sequence of t also. And the result is sequence of t. Now, I could have transformed x here into some other type, and then it would have been this other type. It will be a sequence of u flattened, which is a sequence of u. So flat map has this sequence, has this type signature. It takes, on the sequences, it takes sequence of t, it takes a function from t to sequence of u, and it returns a sequence of u. The exactly analogous type signature for flat map on either would be that it takes an either of LR, it takes a function from R to either of LT. So L stays the same, so we are preferring the right. This is the convention. L stays the same. R is transformed, but the transform function returns an either. Just like here, the transform function returns a sequence, not just a single u, but a sequence of u. Here it returns an either of LT, but the result is not an either of either. The result is a not nested either. That is what flat map is supposed to do. Let's see if we can implement this. We can. We match on this either. If it's in the right, then we call this function, because in the right we have the value r. So we call this function, we get an either. We match on that again. If that is a right, then we return a right. If that is a left, we return a left. So we basically return what that function returns. So actually, I could simplify this code into this. If we are in the right, we just return this either. If we're in the left, we return what was on the left. Now, notice that this left is of this type, and this left is of this type. So we cannot just say this is the same as this. They have different types. Although the values are just inside this L is the same, but this L is being repackaged into a different type without losing information. So this is how we implement either flat map and map for either. The next example is a type constructor called state. Now this type constructor is defined like this. It's a curious thing, but we will see that it is useful. Let's implement pure, map, and flat map for this type. So pure is a function that takes a type A, it takes the value of type A and returns a state with parameters SA. I should have written this as a superscript in this slide, just like I've written it here. The map has a standard signature, so the mapping is performed with respect to the parameter A. The parameter S is not changed, and there's no way to implement map with respect to parameter S. So with respect to parameter A, we can implement map, mapping A to B, and we can implement flat map, mapping A to state of SB, and the result is again a state of SB. So how do we implement these functions? The way to do it is to follow the types. You write down what types you want, and you try to implement them. So we define the type state. This is a little more difficult because you don't say what this type is doing, what is it useful for. Just follow the types, try to see what is given and how you can return the value that is required. So the pure function is required to return a state of SA given an A. So we return a function here that takes an A and then returns an state, which is a function that takes an S and returns a tuple of AS. Well, this is obvious. We just have A and S. We can return only that as a tuple, and that's what we do. There's nothing else we can do to implement this type. Let's look at map. So at map, we have, let's call it SA argument, which is of type state SA. There's an F argument, which is of type A to B, and we are supposed to return state SB. So state SB is a function that takes S and returns tuple of AS. So how do we do that? Well, actually, we need to return a tuple of type B and S. So we take S, and at the end, we should be able to return a tuple of B and perhaps some new value of S. We could return the same value of S here, but probably it's not a good idea. We'll see. So what can we do? How do we get a value of type B? The only way is to use F on some value of type A. So let's say B will be computed as some F of A. What is A? Well, we need a value of type A. The only thing we have here is this SA, which is a function from S to tuple of AS. So we can apply this SA to some value of type S, which we have. It's right here. So the result of SA of S is a tuple with A and some new S. Great. So we have an A, we put it right here. We have a B therefore. And then here we use the new S to return that new S. Why? It would be a shame not to use that thing. We got information from using our arguments, but if we ignore that, it will be information loss likely. This is still an intuition. Right now we have not formulated criteria for the map function to be information preserving, but just an intuition at this point, which turns out to be correct later. But at this point, I just feel that if I ignore this new s, and I could put s here, because I have the value of type s. I could put it here. But that would be losing information. I would be not using something that I have, which something that I got as my argument. So this is my implementation. And similarly with flat map, I have a more complicated situation. But first I apply SA to S, and I get A and new S1. I apply F to that A, and I get a new state B. Now state B is actually a state of SB, which is a function that I can apply to S to get a tuple of B and S. So I apply this state B to this new S1. Again, this is my intuition. I could have applied it to this old S, but it doesn't feel right. That would be, I'm ignoring this new S1. I'm ignoring it. I don't like ignoring information if I'm given it. And similarly, here I want to return this new S2, because if I could return new S1, or I could return even this first S in here. But that would be losing information, because I am given this and I should be using it somehow. And there's only one way of using it. I couldn't exchange this order. I couldn't put S1 here and S2 here, because at this point I don't even have S2 yet. So if I want to not lose any information, there's only one way for me to organize this code. The last example is to define a recursive type non-empty list. And this is defined in the short type notation by this formula. So let's see what that is. We need to define it, and then we need to implement map and concat functions, which are concat is concatenating the lists, and map is just a typical map for a collection. So what does this non-empty list do? It's like a list that we saw in the example, except it's never empty. It's either a value A, or it's a value A and another non-empty list. So it's either one value A, or it's two values A, or it's three values A, and so on. So it's like this infinite disjunction that we saw in this slide, this one, except it starts here. There is no 1 plus. It just starts here. So the list is never empty. There's always at least one value of A in it. That's the difference between non-empty list and the traditional list. So how do we do that? Well, we define the sealed trait and so on. So just like before, the formula is given. So let me just copy this formula into a comment here to be very clear. So there are two case classes in the disjunction. The first one carries just one value A. Let's call this A instead of, let's call this T instead of A, just so that it's convenient for us to compare the code. So the first element of the disjunction has the value T, which is here. The second element has the value T, and also it has another non-empty list. So this is the entire implementation. So how do we now implement map for it? Well, the signature, start with the type signature. Let's see what follows from it. First argument is a non-empty list. Second argument is a function from T to U, and the result must be non-empty list of U. Now, since the argument is non-empty list, which is a disjunction, we must match on it. There are two cases. The first case is this, the second is that. So what do we do in the first case? It's a list consisting of one element. It's this element, this part of the disjunction. Well, we then apply f. There's nothing else we can do except apply f to this t, get a u, and put it into a non-empty list as a head. There's not much else we could do. We couldn't, for example, produce the second one because for this we need already existing non-empty list, and that's not what we want to do. We don't actually have another non-empty list. The only thing we have is this one. All right. Now, in the second case, we have a head and a tail. A head is of type T, and the tail is of type non-empty list. So now we can actually produce the second. We could produce the first one, right? We could just ignore this tail and do the same as we did in the first one. We could always return the same, but that would be ignoring information. That would be information loss. We don't want to do it. So therefore we do not return this, we return the second one. The second one requires two values. The first is the application of f to the head, and that's the only way to get a value of type u, right? So in the ne tail of u, which we require to produce, there must be two values. One is a u, and another is a list, non-empty list of u. Now, how do we get a non-empty list of u? We're not given it. The only way to get it is to apply the map function recursively to this tail. That's the only non-empty list of u that we have. That's not trivial. And that's what we do, therefore. So this implementation works. It's not tail recursive because the map, now if I can just make IntelliJ tell me why, but it's because the map is in the inside of some expression. Right away it's read. Recursive call not in tail position. So this call is in some intermediate position inside of an expression, and so that's not tail recursive. That's fine. We don't care about this at this point. The second function, concat. So it takes two lists and it concatenates them. So how do we do that? Well, we have to match on, let's say we match on the first list. The first list could be just a head. In that case, we return, so that's just a list of one element. So we just prepend this element to L2, which is very easy to do. We return a tail with head given by this and tail given by L2, and we're done. That is directly prepending the list. So basically this takes care of the first case. The second case is a little longer. So we have a non-trivial list on the left as L1 and also maybe a non-trivial list on the right. So what do? We'll take the head, put it here, but then the tail must be the concatenation of this tail and whatever is left. So we use the concat call recursively here to produce the tail of the list. So this is an implementation that we are looking for. So basically that concludes the worked examples for this tutorial. Here are some exercises that I encourage you to do in the same way that I was showing the worked examples. So in these exercises, what kind of problems can we solve? Now this goes over all the problems that we can now solve using the tools we found. Let me see. I have a slide with that. We can use the short type notation for reasoning about types. So we can convert short type notation into case classes and back. Now, Given a fully parametric type, we can decide whether it can be implemented in code. And computer scientists who do theory of types and functional programming say that this type is inhabited. In other words, the Curry-Howard's proposition, CH of t, is true. There exists a value in the program, there exists a value, has been computed, of this type. This is what is called inhabited. And if it can be implemented, generate the code. So this is the algorithm I'm linking here. There's a whole overview of these algorithms. And also there's this Curry-Howard project, which I will demonstrate right now. Another thing we can do is what was in the first part of the third chapter, is if you take an expression, you can infer the type it can have. Now, there is an algorithm for this too, which is called the Damas-Hindley-Milner algorithm, and I'm giving the links here. We can decide type isomorphism. We can decide whether some types are equivalent. We can simplify type formulas using the arithmetic Curry-Howard correspondence. Well, I call it the arithmetic Curry-Howard. This is not accepted terminology in computer science, but I found it very helpful to think about it this way, as arithmetic correspondence. As I showed, the logic correspondence does not give you type isomorphism information, but the arithmetic one does. So using these tools, you can compute the necessary types before you start to write code. And when you start writing code, you're guided by the types, and in many cases, it helps you write code correctly the first time. What are the problems that we cannot solve with these tools? Well, we can not automatically generate code that satisfies some complicated properties, like, for example, isomorphism. This is what I showed you when we were implementing the state code for flat map, for example. There are several possibilities of what to do. There are several implementations, and I'm using this intuition about information loss, but so far I have not formulated specific exact criteria that these functions must satisfy, and automatically generating code for these functions that satisfies these criteria is something that we cannot do using these algorithms. These algorithms will just give you some implementation or all implementations, but they will not be able to check equations or such things as type equivalence. And the second thing you cannot do is express complicated conditions. For example, we defined a list that is not empty, but we could not define a list that is sorted. There's no way to define a type that automatically sorts the list. You can write code that sorts the list, for sure, but you cannot have a type that somehow by itself is not going to compile unless the array is sorted. See, that is impossible. The types that we have worked with are not powerful enough for that. There are more powerful type systems that are called dependent type systems, and programming languages like Coq, Agda, and Idris. These are the languages that implement dependent types, and they can express such conditions as the list or array is sorted, or has a certain length and is sorted, or something like this. You can have non-trivial conditions enforced by types. Here we have, for example, the condition that the list is not empty. We enforced it by type. You could not compile a program using this type, an e-list. You could not compile and run compile a program unless the list is non-empty. So this type system of Scala and also Haskell and OCaml and F# and Swift and Rust and such languages, the type system of these languages is powerful enough to express that the list is not empty, but not powerful enough to express that it is sorted, let's say. Another thing I'd like to talk about, let me demonstrate first the Curry-Howard project. I will then talk about this as a conclusion. So in the Curry-Howard project, I have started implementing a Scala function, which is called implement. And this function looks like magic. So here's how I use it. These are tests, actually. These are unit tests. They run and pass. So for example, I say def f1. So I define, as if I define a function. I specify its type, for example, from A to B to unit. Now this function cannot do very much. It's a pure function, so there are no side effects. The only thing it can do is ignore A and B and return a unit value. And that's what the tests check, that you give it various values and it returns unit. You give it all kinds of different types, it ignores them and returns unit. Another example is here. Function with two type parameters A and B. It takes a value of type A, it takes a function from A to B and returns a value of type B. So the only way to write code for this function is to take this parameter, which is a function, apply it to this parameter, which is A, get a B, and return that B. Since this is the only way to write code for this type, in other words, the only way to implement this type, I want to do it automatically. So this function does it. So the result of writing this is as if I have written the code for this function, and then I have tests that check that it works as if I have written that code. Another example here is a more complicated function type, which is also implemented automatically. And I have a test that shows that, for example, yeah, there's another syntax, of type. So there are two alternatives right now implemented. Of type, which works like this. Where do I see of type? Here, for example, I have of type. So this is the same signature as we had in the pure function for state. Take A, take B, return tuple AB. So this can be automatically generated. This is an alternative syntax that I implemented, of type. So you say def f of AB equals of type. So the code that is the only one possible of this type. That is what this function does. So basically it generates the code that we had here. This code is generated automatically because of the algorithm that checks that the type can be implemented, and if so, generates the code. Another example, take A, take a tuple of this type, so function of A to B, from A to B and C, and return B. Now here we have to ignore C. There's no way around ignoring C. There's nothing we can do with C. We can only take this tuple, we take the first part of this tuple, apply that to A, get a B, return B. So C is ignored. That's all right. Sometimes you ignore arguments. This is, of course, certain information loss, but this is the only way to implement this type. Another example. From A to this tuple to this tuple. Now here we don't lose any information, and this type also can be implemented automatically. And there are some more examples like this. So this is work in progress. I just wanted to show you that in certain cases these functions can be useful, like for example in the cases we have seen, the reader, the state, that can be generated automatically, flat map and map for them and so on. this is work in progress, and I will continue implementing these algorithms so that we can automatically generate as much as possible. So let me conclude with a discussion of the implications of Curry-Howard correspondence for programming languages. It is not just for programming code, but also for design of programming languages. It's a much more important consequence of discovering the Curry-Howard correspondence. So as we have seen, the Curry-Howard correspondence is a map from a type system into a certain logical system, a system of axioms and derivation rules, and such that certain logical propositions are valid or are theorems, and others are not theorems. And correspondingly, those that are theorems can be implemented as functions, and others cannot be implemented. So one consequence of this is that if you have a good logic that is powerful and can have a lot of theorems, a lot of interesting, non-trivial theorems, then you can implement a lot of interesting and non-trivial functions in your programming language. And all these functions will be automatically checked correct. If you have a logic that is limited, that cannot derive a lot of theorems, then you also cannot do a lot on your type system in your language. Another consequence is that if your logic is inconsistent, if it can derive a contradiction, then your program will crash. It means that you put some type into the wrong function and it will crash at runtime. Your compiler won't be able to catch it. So it is very important that that we understand that there's a mathematical principle behind inventing programming languages. And this principle is that the type system of these languages must correspond to a good, consistent, non-contradicting, and fully featured logic, so to speak, with all logical operations that are available. So these programming languages have been designed with this in mind. They have been designed with the idea that we have a certain logic, and so this logic has certain operations such as or, and, implication. And so these operations should be available in the type system. And so the type system of these languages has function types, it has disjunction types, or sum types as they are also called, and product types, or tuples, or conjunction types. Whereas languages such as these do not have, for example, the disjunction types. They do not have the constant true in the logic, which is the unit type. These languages do not have the unit type. You could not say, let x be of unit type, and then put x as argument into some function. You cannot say that in these languages. Python and other languages in this list essentially have only one type, which represents any kind of value that is possible. And so these languages are mapped into incomplete logics. These to logics without or operation, without the true or false constants. And this is mapped to logic with only one proposition, which is we can compute something of some value, and that's it. These logics are very limited. There are not a lot of theorems in them, and of course more in these than in these, but type system makes a difference. It prevents errors. So the mathematical design principle is that mathematicians have studied logics for a long time. They found interesting logics, and they found a minimum set of axioms for them. Let's use that. Choose one of the logics that mathematicians have found, and they found a bunch of them. They're modal logics, temporal logics, linear logic. There are all kinds of variations on this theme. There are different logics, so choose one of them. The one we have been working with is called intuitionistic propositional logic. Well, this is a very technical term. I prefer to call it constructive logic. But these are also other possible logics. For example, temporal logic is at the basis of functional reactive programming. So the idea is to implement a language where this is the logic of types. And if you do that, then you get the stream type for free. And it's very interesting to see that. Linear logic has been used to model resources, such as memory, ownership of pointers. One thread has ownership of this pointer, another thread has ownership of that pointer. If you have this in your language, you can do interesting constraints on your program and prevent errors. So the mathematical principle is that you take a logic that mathematicians have studied, you take its axioms and its rules of derivation. Mathematicians have found the minimum sets of axioms. That was their game. They like to find what is the minimum set of axioms for a given logic, such that you still derive the same theorems. That's very interesting for mathematicians. So they already did all this work. Let's use it. Take that set of axioms and rules of derivation, and for each of these, provide a type constructor of some kind, or a language operation. And you get a programming language out of this. And put this at the foundation of your programming language. Add other features, of course, but that should be the foundation. You should not remove things like this. If there's an axiom in the logic, do not remove it. You will limit your language fundamentally and irrevocably. That is the lesson of the Curry-Howard correspondence. Let's use the centuries of experience of mathematics. It tells us what is actually useful, what are the operations that are useful, what are the operations that are not necessary, what is the minimum set of operations that is required. Do not remove things from the minimum set that's required. Don't try to make a logic that doesn't have a true or false constant, or doesn't have an OR operation. That is unnecessary limitation that is very hard to lift. Another illustration of why mathematics is useful is that I had to implement this exists sum as a helper method because the testing library does not have it. Let me show you what I found. So there is this link where there's a discussion of why there's a for all in the library but not exists in the library. And the reason was that no user has requested it yet. Now, of course, no user has requested. That's not a valid reason for excluding a basic mathematical construct. If you have a for all, you must have an exists. Or you need to have negation, but negation is not there either. So logic that has a for all quantifier but does not have an exists quantifier is fundamentally limited. It's a basic mathematical principle. It should not be necessary to wait until users request it. It should be obvious that this is necessary. It should be at the foundation of the design. And of course, the real reason there is no exists is that it was hard to implement. And the design was such that it was not easy to implement. The design should have been informed by mathematics and not by what users happen to want at this point. This is among the lessons of mathematics and of Curry-Howard correspondence. This concludes the third chapter.